So a few outcomes of the rate laws section here. We want to be able to describe what a rate law is and what it looks like, how to use them to calculate reaction rates, and then how to think about reaction orders and derive rate laws. That's the goal at the end of this subsection. The rate laws are these really useful expressions that relate the concentration of a reactant to the actual reaction rate. So it's just an algebraic expression. We sometimes call these differential rate laws. And there's actually no fundamental way to derive them. They are experimentally derived. That means we need experimental data to understand what the actual rate law, or the relationship between concentration and rate, is for a particular reaction. So let's just consider the generic form of a reaction where we have A plus B make some products, and the lowercase a and b are the stoichiometric coefficients to balance that individual reaction. So previously we showed that we could write up the rate algebraically for the balanced chemical reaction like this. So the disappearance of A relative to T equal to the disappearance of B relative to T. But how do we express that in the form of a relationship between the concentration and the actual rate? We do that using a rate law. The rate law looks like this, where we have some constant K, this is the rate constant at a fixed temperature and condition set, times the concentration of A raised to this power M, times the concentration of B raised to the power N. This whole expression is the rate law, and it allows us to relate the actual rate to changes or different concentrations at any moment in time. The exponents here, M and N, are called reaction orders. And those are typically whole numbers, positive numbers, but they can sometimes be fractions, negative, or zero. And the reaction order essentially indicates the sensitivity of the rate, because that's on the other side of the expression over here, to those individual concentrations, right? If M here in this expression is 0, then that means that the rate is independent of the concentration of A. If this is 1, then it means it depends linearly, right? As A increases, rate increases at the same rate. If that's a 2, then that means as A increases, rate is increasing exponentially or quadratically, 3, etc. So those are considered the reaction orders. They dictate the sensitivity of the rate to those individual reactant concentrations here, A and B. So let's look at a couple examples. So the first one here is this decomposition of H2O2, which we've talked about in the past. And the rate expression for that, experimentally determined, is that the rate is equal to that constant, right, which is independent of concentration. That's just its own constant, a fixed number, times the concentration of H2O2 raised to the first power. So that means the reaction order for this overall reaction is called first order because of that exponent equal to 1. So you'll often see me either write first order, or sometimes I'll just write 1 to the degree sign here, which indicates that's a first order reaction. What does that mean? Well, it just means that as I increase the concentration of the reactant, H2O2, the rate of that decomposition increases linearly. So if I double that concentration, I double the rate. If I triple the concentration, I triple the corresponding rate. So a second example is the reaction here. So rate is equal to K times the concentration of C4H6. It's not important we know what the actual balanced reaction is. We just have the experimental rate law. But we can see that that's now raised to a power of 2, which means that this is a second order reaction. What does that mean in experimental space? Well, it means that as we double the concentration of this, then we are quadrupling the rate, because that's the exponential relationship there. And let's look at this final example here. So rate is equal to K times hydrogen ion concentration times hydroxide ion concentration. If nothing is written as powers, then it's implied, just like any algebra, that those are 1s. So what would the overall reaction order be here? Well, we would say that the overall reaction is second order because of the sum of those two exponents. They're both first order, but we could also say that the reaction is first order with respect to hydrogen ions and first order with respect to hydroxide ions. So it's an important distinction here. If we have more than one concentration of reactant in the rate law, then the sum of their individual orders is the overall order, but we could also talk about their individual orders. So if this is first order in proton concentration, that means if I double it, rate will double. Same is true for hydroxide. But if I double both of them, then that behaves as a second order reaction and the rate will quadruple. So this is an example graph from the OpenStax textbook. Take a look at this, pause the video, and see if you can make sense or actually produce the answer, and then unpause the video and I'll walk you through it real quick. So remember I said rate laws have to be experimentally derived. There's no actual fundamental relationship that tells us about the reaction simply based on its balanced form. You can see that there's no stoichiometric coefficients to balance this. It's balanced as is. But experimentally we find out that the reaction is second order in NO2 and 0th order in carbon monoxide. So we could write out an expression that says rate is equal to rate constant that's always present times the concentration of NO2 raised to 2, because that's what second order means, times concentration raised to the 0th power, which means that that whole term goes away and we can simplify the expression like this.